So let's take a look at the synthetic division of polynomials. We've got -2, 5, -6, -28, and -2. Right, so we bring down the 5. This becomes -10. This becomes 32. That becomes -8. So we write this answer as 5x squared minus 16x plus 4 minus 10 over x plus 2. We've got something called the remainder theorem, and we can actually rewrite this as 5x cubed minus 6x squared minus 28x minus 2, that's our original, is equal to x plus 2 times 5x squared minus 16x plus 4 plus a -10, because there's that minus sign. This is actually called the division algorithm. I can take my f of x and I can set it equal to the thing I'm divided by times that answer I get, because that's what division is, plus my remainder. This is what it looks like as an algorithm. So for any polynomial and any complex number k, remember that a complex number can include an I as well. We've got some unique polynomial, so that here's that formula I just wrote. My original one is equal to the thing you're dividing by times the answer you get plus your remainder. And that brings us to the remainder theorem, saying that if we have some polynomial and we divide by x minus k, the remainder is equal to f of k. So we can actually calculate f of k by doing synthetic division. And that's what we'll do next. So here we're using the remainder theorem and synthetic division to find f of 4. K in this case is therefore equal to 4. So we can set that up. There's 0x squared, so I need to make sure I put that in. Oops, I don't need that plus sign. Twelve times 4, that's 48. So this is my remainder. So f of 4 is equal to 17. Now, why would you do this? Well, I could have plugged that all into my calculator, but it probably would have taken longer because I've got so many exponents that I have to deal with. This actually got done pretty quickly. Now we're going to use synthetic division to test for zeros. The reason that you might want to find zeros is so that you can graph these functions. You can factor them. You can find out, like, for example, at how many seconds does the projectile hit the ground. That's why we might want to find zeros. And what we're doing is we're actually finding out, is this value, this x value, a zero of this function? So if we take a look at the first one, put in a 0 for x because it's plus 0x. So I've done the synthetic division. How do I know if it's a 0? Well, remember that this last number here is the remainder. If the remainder is equal to 0, then k is a 0 of the function. This one's negative 14, so 2 is not a 0 of this function. Let's try the next one. So now my remainder is 0, so negative 3 is a 0 of the function. This is our last example, and I'd like you to notice that k now includes I, the imaginary number. We can still do this. So we still bring down the 1. 1 times 1 plus 3i is just 1 plus 3i. Oops, that's not an I, that's a t. There we go. So when we combine these, we get 0 plus 3i. From here, we need to multiply those two together. And I'll do that over on the side here just so that you can see it. Now you have to remember that I squared is equal to negative 1, so this is negative 9 plus 3i. So that's what you get when you multiply these together. So this gives us negative 3 plus 3i, and now we have to multiply those together. This 14 becomes negative 12 minus 6i. And I'll multiply those. So that's 20. So we did all that, but we found that 1 plus 3i is a complex root of this equation. So in the last problem, we had a real number root. That's going to show up as an x-intercept on the graph. this one, this complex root, will not show up as an x-intercept because it's an imaginary number, but it is something that we should consider as a root of the function.